What is the number of bit operations required to compute product of two polynomials? The problem is to find an upper bound for the number of bit operations required to multiply a polynomial sigma ai x raised to I of degree less than or equal to n1 and a polynomial sigma bj x raised to j of degree less than or equal to n2 whose coefficients are all positive integers. That is, ai and bj are all positive integers less than or equal to m. For convenience, we assume that n2 is less than or equal to n1. Now, the given polynomials can be expressed like this, since the degree of the first polynomial is less than or equal to n1 and the degree of second polynomial is less than or equal to n2. Also note that each coefficient ai and bj are all less than or equal to m. Now find the product of these two polynomials. We need to calculate the coefficient of x raised to v, where v varies from 0 to n1 plus n2. We can see that the number of multiplications required in each stage is less than or equal to n2 plus 1 and the number of additions required in each stage is less than or equal to n2. Since each number being multiplied is less than or equal to m, that is, we are calculating products of the form ai into bj at each stage, where each number ai and bj is less than or equal to m. So, the number of bit operations required for each multiplication is less than or equal to number of bits of m into number of bits of m. That is, number of bits of m whole square. And we know by the formula for number of bits, this quantity is equal to greatest integer function of log m to the base 2 plus 1 whole square, and that is less than or equal to log m to the base 2 plus 1 whole square. Since at most n2 plus 1 multiplications are required to compute the coefficient of x raised to v, the number of bit operations will be bounded by n2 plus 1 into log m to the base 2 plus 1 whole square. Now, for addition, at each stage we will be adding a term of the form ai bj to the partial sum of n2, at most n2 such numbers. The first number being added will be of the form ai into bj, since each number ai and bj is less than or equal to m, this product will be less than or equal to m square. The partial sum, that is the second number being added at each stage, will contain at most n2 such numbers, numbers of the form ai into bj. So, the partial sum will be bounded by n2 into m square. Hence, the number of bit operations required for each addition will be less than or equal to maximum of number of bits of numbers involved in the addition. That is, maximum of number of bits in m square and number of bits in n2 m square. So, the number of bit operations for each addition is less than or equal to number of bits in n2 m square, and that is bounded by log of n2 m square to the base 2 plus 1. Since n2 such additions are needed at most, so the number of bit operations required will be bounded by n2 into log of n2 m square to the base 2 plus 1. Thus, the number of bit operations required to compute the coefficient of x raised to v is at most n2 plus 1 into log m to the base 2 plus 1 whole square. This is the number of bit operations required for multiplication, and this is the number of bit operations required for addition. while computing the coefficient of x raised to v. Thus, since there are n1 plus n2 plus 1 values of v, since v runs through 0 to n1 plus n2, we have n1 plus n2 plus 1 values for v. So, our estimate for the time required for the bit operations required for polynomial multiplication is bounded by this quantity.